tell us about yourself. You are going to introduce yourself as you do.
Perfect. Okay, so thank you for inviting me. First of all, I would like to say something about your presentation. It was quite fascinating that you briefly introduced quite many research. It was really fascinating to see all of them. So today I am joining this conference from Norway. It's 1 hour by plane from Oslo towards north. It is 7 centigrade Celsius outside currently, and it's 6 p.m. In Trondheim. So my name is Emir Ahmet Oguz, and I would like to share my screen first. Okay, my name is Emir Ahmet Oguz. I'm currently working as a geotechnical engineer at Norwegian Geotechnical Institute. Today, I would like to make a presentation on the effect of soil heterogeneity on susceptibility of shallow landslides. This work was published in Landslides last year. This was a part of my PhD work at NTNU in Klima Digital project. This is the content of today's presentation. I will first go through background and motivation of this research. Then I will talk about the physical-based landslide susceptibility models, but I will mainly talk about introduce the three-dimensional probabilistic landslide susceptibility model, which was developed for this study. Later on, we will see the special variability impact on landslide susceptibility and the capacity of the developed 3D PLS model to capture these impacts. Later, we will go into a case study, and I will share some results that even I didn't put it in the paper, and I will finalize it with very brief major conclusions. As we all know, landslides are worldwide problems causing catastrophic consequences such as fatalities, injuries, economic losses, or environmental damages. This figure shows the worldwide distribution of fatal landslides only in between 2010 and 2014. The same data set shows that in between 1995 and 2014, almost 9,000 people died every year. And when we see the data set, majority, almost 60% of these landslide events are associated in time and place with extreme rainfall events. Here, one example is shown from Norway. It's very close to where I am right now. So these rainfall-induced landslides pose great risk to society due to their high frequency of occurrence and their capacity to evolve in destructive debris flows. If you see this figure here, you can also compare that there is a house here. It's like a two-story house, but this debris is quite destructive. There are also some reports by Intergovernmental Panel on Climate Change, both Assessment Report 5 and Assessment Report 6. They both state that there will be more intense and frequent rainfall events at most parts of the world, excluding some parts. And this increase will also increase the risk associated with rainfall-induced landslides. And this increasing risk requires us to have efficient landslide hazard assessments. And one of the major challenges in accurate spatial and temporal prediction of landslides, one of the major challenges is uncertainties, and there exist quite many sources of uncertainty in this field. For example, lack of field and laboratory investigations, inherent natural variability of the soil. It might be model uncertainty or some uncertainty about the initial hydrological conditions, which is not surely like 100% known in any research from my perspective. And in landslide assessment originates from spatially variable geotechnical and hydrological parameters. This is the inherent natural variability of the soil. And if we do not include them, if we avoid these uncertainties, and if we only employ deterministic values, the results might be either unrealistic or too conservative. Physical-based landslide susceptibility models are widely used since 2000, and they are used over large areas from 500 square kilometer to 500 square kilometers. In this table, some of the landslide susceptibility models are tabulated, and in general, these models combine slope stability model and hydrological model. Hydrological model is mainly responsible for simulating infiltration into ground, and provide the hydrological response of the slopes to slope stability model, in which it performs the slope stability calculations either based on infinite slope stability method or some three-dimensional slope stability methods to predict the landslides. When it comes to uncertainty in the landslide modeling, some of these models have capacity to include the uncertainty in the model parameters. However, they consider a single random variable approach, which means that the soil is uncertain but homogeneous. In this case, we cannot investigate the special variability impact, which means heterogeneity over space. Therefore, I developed a three-dimensional probabilistic landslide susceptibility model to investigate this. Now I will briefly introduce this model. This 3D PLS stands for three-dimensional, it's probabilistic, and landslide susceptibility model. It's a Python code developed for probabilistic landslide susceptibility assessment for a given rainfall event, and it accounts for special variability of the model geotechnical and hydrological parameters. Here, this figure shows a 3D illustration of the landslide body with a single grid column with the forces. So it generates ellipsoidal sliding surfaces, three-dimensional sliding surfaces over the problem domain and calculates the factor of safety of each. The model in general couples the slope stability model and hydrological model in a statistical framework. So in slope stability model, it's three-dimensional extension of Bishop's simplified method of slope stability analysis was utilized. And in hydrological model, Iverson's linearized solution of Richard equation for tension-saturated soils were utilized. I didn't have time to include unsaturated soils, but it can be integrated later. And the uncertainties in the model parameters were propagated to the model output by using Monte Carlo method. The randomness, the special variability of the soil parameters are modeled explicitly by using random field approach by using two-dimensional Gaussian and log normal random fields. In this figure, plane view and side view of the three-dimensional sliding surface is illustrated with its corresponding dimensions. If this is a landslide-prone study area, which is discretized into cells, grid cells, the model generates ellipsoidal sliding surfaces centered at each cell. In this slide, I just showed like 5 sliding surfaces with its corresponding dimensions. And this model performs stability calculations over the problem domain. Then each cell in this domain intersects with a multiple of like many of these ellipsoidal sliding surfaces. And the model assigns the minimum factor of safety of these intersecting ellipsoidal sliding surfaces to this specific cell. Then when we perform the 3D PLS model, it gives the factor of safety map for each Monte Carlo simulation. And by using these maps, we can get mean factor of safety and we can get probability of failure, which is the probability of having a factor of safety less than 1 in the study. And the probability of failure was used as a measure of landslide susceptibility, which means that higher the probability of failure, higher the susceptibility is. Okay, the special variability was explicitly modeled by random fields. To generate random fields, a probability density function is used. It might be normal, log normal, or any other probability density function based on the data that you have or based on the assumption. In addition to that, an autocorrelation function is also utilized. Here, I only showed an ellipsoidal autocorrelation function. The correlation of parameters at 2 special coordinates, Lm and Ln, here is based on the correlation length, Lx and Ly. These are the correlation length. It's also called scale of fluctuation in some research in the X and Y direction. And also it depends on the separation distance in tau Y and tau X, the distance of separation in X and Y direction. And using this explicit approach, we can generate random fields. For example, in this figure, different random fields based on different correlation lengths are illustrated for a friction angle with a mean of 30 and standard deviation of 4.5. When the correlation length is infinite, it means that the soil is homogeneous and the friction angle over the problem domain, 100 meter wave, 100 meter problem domain, is constant over the problem domain. When we start having some correlation length, we see that the value is changing over the space. And when it's, for example, 50, 10 meter, we see that there are some darker zones over the problem domain. These darker zones are having weak, lower values of friction angle, which will later dominate the factor of safety of the slopes. Such random fields are generated with 3D PLS model and used in the landslide susceptibility assessment. But first, we should validate the model. In the slope stability model, three-dimensional extension of Bishop's simplified method of slope stability was utilized. And to validate this, I used three benchmark problems, as shown in this figure. The first validation problem is here, a spherical sliding surface in a purely cohesive soil. The second problem is again a spherical sliding surface in a soil with cohesion and friction angle. The third one is the most complex, in my opinion, because there exists a weak zone at certain depth, which results in truncation of this sliding surface. And there is also groundwater table. We compared the results obtained by 3D PLS model and from the literature, and we have seen that the model results are within the range of reported values in the literature, so that we validate the capacity of the slope stability model. Then it comes to investigating special variability impact on landslide susceptibility, and of course, validation of the 3D PLS model to capture these effects. To do that, I used a simplified validation problem geometry. In this figure, you see the problem geometry, plane view, and the three-dimensional view. It's 100 meter by 100 meter domain. The thickness of the soil is 2 meter, shallow, and the soil is inclined by 25 degree. And the problem parameters. So I investigated both drained and undrained case. In drained case, cohesion and friction angle parameters were modeled as spatially variable. And in undrained case, undrained shear strength parameter was modeled by spatially variable. In this study, there are three coefficient of variation level: uncertainty level, low, moderate, and high. And I investigated 8 different correlation lengths for, from 0 to 1000. 1000 might be assumed as homogeneous over this problem domain. And for the validation purpose, so I used finite element-based Plaxis model simulations to validate the results that we obtained from 3D PLS. In addition to Plaxis model, I also wanted to compare if we can compare the results of 3D PLS with another cell-based approach. Then I made another model which I will call it cell-based model, which uses the same hydrological model and same statistical framework. The only difference arises from the slope stability model. Instead of employing three-dimensional slope ellipsoidal sliding surfaces in this model, it employs infinite slope stability method for each cell individually. For example, Trigares is doing it. So then I will also compare the results obtained by 3D PLS with this cell-based model. As you all know, Plaxis is explicitly accounting for the complex processes that is included in the landslide initiation, such as the shear band, the propagating of that shear band, and until failure. Therefore, when we have a factor of safety obtained by Plaxis, we can say that, okay, this is the global factor of safety of my problem. In 3D PLS model, it provides, instead of a single factor of safety value, it provides a map of factor of safety. Then to relate the map of factor of safety to the global factor of safety, we use the minimum factor of safety over the problem domain. This minimum factor of safety gives us the most critical ellipsoidal sliding surface over the problem domain. When it comes to cell-based model, it performs the calculations for each cell individually. Therefore, we cannot take the mean. As the Griffiths and Fenton also suggested, I just took the harmonic average over the problem domain to represent the global factor of safety of this problem. I first performed some deterministic model simulations to see how the results are varying based on the model, finite element based, Plaxis model, cell-based, and 3D PLS for drain and undrained cases, and all of them results in pretty much the same factor of safety value. Then for the variability case, for each variability level, low, moderate, and high, and for each correlation length, 1000 Monte Carlo simulations were performed. At the end, I took the average of the Monte Carlo simulations to calculate the mean global factor of safety. This is just to compare the models. I just averaged the global factor of safety values over the Monte Carlo. And we can see the results for drain case. In this figure, you see the correlation length on x-axis and mean global factor of safety of this problem domain on the y-axis. There are three curves which represent three variability levels: low, moderate, and high. These are the results obtained from Plaxis, and each point in this figure is 1000 Plaxis model simulations. It was quite intense work. First observation obtained from this graph is that the factor of safety values at a specific correlation length decrease as we increase the variability level. From low to high, the factor of safety decrease. The other observation is that when the correlation length is 0 meter, which means there is no special dependence, the factor of safety values are high. This was attributed to the fact that if there is a weak cell, it is highly possible that the next cell is stronger. Then that cell will support the weak cell, then the factor of safety will not dominate it by that weak zone. But as we increase the correlation length up to 50 or 100 meter, what we see a drop in the factor of safety. This is due to the fact that when you increase the correlation length, the weak zone in the problem domain is getting larger and larger, and it starts dominating the factor of safety that we get, and the factor of safety values decrease. The rate of decrease, the value of decrease here is also depending on the variability level. Higher the variability level, higher the decreases. So when you further increase the correlation length, what happens is that you start reaching homogeneous case, and the weak zones are not dominating the factor of safety of this problem anymore. This is the results from factor of safety by the Plaxis model simulations. Now we can see how is the 3D PLS and cell-based model results. In these figures, in A, we compare the Plaxis results with cell-based model approach, and B, we compare the results of Plaxis with 3D PLS model. So here in A, we see that the cell-based model approach is not able to capture the special variability impact. This is because of the fact that this model employs infinite slope stability model for each cell individually, and taking harmonic mean or any other. We also tried some other assumptions to relate it to global factor of safety. None of them worked really. So because it's not investigating as a zone, it's just done by for each cell individually. But in 3D PLS case, we have observed the same behavior based on the correlation length, based on the variability level. There is no perfect fit in this figure, I know, because we have used a set of ellipsoidal dimension in this problem. But our aim was to show that this model is capable of capturing these effects rather than achieving a perfect fit. So in this way, we validated that, okay, this 3D PLS model can capture these special variability impact. The same simulations were also performed for undrained case, and the corresponding figures can be seen at the bottom. We observed the same behavior from the Plaxis model simulations, and again, the cell-based model couldn't capture, and the 3D PLS model had the same behavior as we have in Plaxis model. Here in this study, what we see is first, how the spatial variability impact the landslide susceptibility and the capacity of the 3D PLS model to capture these impacts. So this 3D PLS model is an open source code. I already put it in GitHub. So the paper had version 0, but I also improved it. Now it also includes parallelization with new code framework, which made it much more efficient in this case. And you can just download it, modify it as you wish, or contact me for collaboration. After validating the model, now it comes to implementing it on a case study. We selected a zone in the central Norway. There is a city called Kvam, and this area had lots of landslides after a rainfall event in 2011. After this is the aerial pictures in 2010, and this is from 2011. And I performed 3D PLS model simulations over this small extent. It's 500 by 1 kilometer in dimensions. So what we can do? We can say, okay, I will follow deterministic approach, and I will just use one single value and one single simulation. And this is the factor of safety map you will get with deterministic approach. What we see here is there are some zones with factor of safety of 1.2 and 1.1. This is the zone. Then, okay, we can perform probabilistic simulations with 1000 Monte Carlo simulation, and we can plot the mean factor of safety map. But this is the case with point variability, in which we used single random variable approach. The soil is homogeneous, but the parameters are uncertain, which means that in each Monte Carlo simulation, we used another set of parameters, but the parameters are constant over the problem domain. In this case, there is very small extent with a mean factor of safety of 1.1 and between 1.1 and 1.2. When it comes to spatial variability, we did the same simulations with 1000 Monte Carlo simulations, and we plotted the mean factor of safety map by using spatial variability, by including spatial variability, which is the heterogeneity over the space. Then we have seen that there is much weaker zone, much critical zone here, which has a factor of safety between 1.1 and 1.0. I checked the values, it's quite close to 1. We can maybe see the histogram from the point variability and spatial variability, and this will be the histogram of the factor of safety values obtained from two variability approach. What we see is spatial variability results in a shift of the histogram towards left, towards 1.0, and results in more critical zones over the study area. Okay, this is something that we can see. Then let's see the probability of failure. This is the probability of failure map for the point variability, and this is the probability of failure map for spatial variability case. Now, this was quite surprising for me, because this point variability was providing us higher mean factor of safety values, but for some reason it also gives us higher probability of failure. And in spatial variability case, although we have lower mean factor of safety values, we have lower probability of failure over the problem domain. Okay, if we see the histogram of the probability of failure values, what we see is that the point variability is giving somehow like higher values of probability of failure over the domain. Then I said, okay, let's see the factor of safety values of this specific cell over this domain. And the histogram of the factor of safety values look like this. Then I suddenly remember the figure from Susan Lakas and others, and there are similar figures, which shows that although this spatial variability provides us a much more critical mean factor of safety, the proportion of this curve under 1.0 is quite less compared to the point variability. Point variability case, we have, okay, somewhat higher values of factor of safety, but the proportion of this below 1.0 is quite high. It's also illustrated in this figure. Later on, I just compared the 3D PLS model results with conventional cell-based approach. In this figure, at the top, you see 3D PLS model results before and after rainfall event. in most of the cases in research studies, most of the time they only show the situation after rainfall, but they do not mention about the situation before. And the cell-based model, here on the left, we have the situation before rainfall and after rainfall condition on the other side. When we see the maximum probability of failure, we have seen that cell-based model results in quite high probability of failure, almost 22.8%, even before the rainfall event. It was quite high in my opinion, and 3D-PLS model resulted in fairly low values, around 8.8. And after rainfall, like it goes up to 22, and cell-based goes up to 30, 32 almost. Another thing that we observed is that the probability of failure values are quite smoothly changing in 3D-PLS model because we are investigating an ellipsoidal sliding surface rather than cell-based. And here we have very rough changes of probability of failure values over the problem domain, which makes it a little bit unrealistic. Then what we did? Then we calculated the performance parameters, true positive rate, false positive rate, accuracy and precision and others. Then we draw the receiver operator characteristics curve. But here, to predict a landslide, this is not factor of safety. We cannot say that, okay, factor of safety less than 1 is failing. This is probability of failure. Then there is no common understanding of the probability of failure, which means that we cannot say if we have a certain probability of failure, it is failing or not. Then I used different probability of failure limits to decide it. These are like if it is 5%, a cell is instable if the probability of failure is higher than 5. Then the results show that the 3D-PLS model provided higher ratio of true positive rate to false positive rate than the cell-based model for all values of the probability of failure limit. This is a way of showing the performance of the model. It provided higher accuracy and precision compared to cell-based model for all values of the probability of failure limit. Then we concluded that 3D-PLS model is more accurate and precise in predicting despite its low values of true positive ratio when we compare it to cell-based model. Now I will quickly conclude my presentation with 2 major conclusions. First, spatial variability of the model parameters might significantly affect the landslide susceptibility. And this was shown in this study, and this spatial variability should be accounted for in the simulations. And when we account for spatial variability, we can obtain more reliable and accurate landslide predictions, which might also improve the landslide early warning system later on. And we have shown this by the developed 3-dimensional probabilistic landslide susceptibility model. Thank you for your attention. You can see my contact information. Please just send me an email if you have any questions or if you are interested in collaboration. So here there are the references that I have used in this presentation, and thank you for your attention.